Hello, and thank you for joining me for a second Data Analysis Bootcamp class. I wanted to quickly recap our mnemonics from the last class to reinforce what we had learned the last time. So remember, we talked about our data analyst friend, and really his job as a data analyst, well, to really summarize, there's so much information out there in the world, and his job is really to refine down that information, to refine down the data of the company into more manageable, useful insights instead of just clutter of information. He's really trying to organize it, refine it, and turn it into those useful bite-sized insights that can support decision making with his business partners. We talked about our really smart friend who was wearing the pattern suit, and he was wearing that pattern suit to represent and help us remember that we really want to understand patterns and trends of our industry, of our business, of maybe the economy as a whole. Okay. And as we were looking at him, there's all this data floating around. He was going to use all of that data to make data driven decisions. When we looked at him again, he was holding a big bag of money, and he let us know that he got that big bag of money from discovering opportunities outside of his business that he was able to identify and become very profitable by doing so. He also had those really big, ridiculous glasses on, if you remember. And those really big glasses that he was wearing was to help him look internally, introspectively, kind of looking down to see if he could kind of use his X-ray glasses to find inefficiencies, look for ways to optimize his business, find ways to really remove those bottlenecks, and really maybe again we talked about maybe looking for new technology to help make the operations more efficient. Okay. And we also the weirdest thing that we talked about, and the weirdest thing in this case is a rabbit in a spacesuit. So we talked about if we wanted to understand why that rabbit is wearing a spacesuit, we'd start with this theory. Why could he be wearing a spacesuit? Oh, he's going to go to the moon. We wanted to start looking at direct our analysis to start looking for that spaceship if he'd gone to the moon. Okay, so we wanted to do that. We also want to understand, really start to understand the anomaly of the rabbit wearing the spacesuit. Not just, that spacesuit, we want to understand why on a deeper level, understanding why he could be wearing that spacesuit, right? And just like identify anomalies in the business, we want to understand really why they're occurring so that we can better prepare ourselves for the good and bad anomalies because both can carry risks towards our business. And then we wanted to make sure that we evaluate our decisions, right? We want to evaluate, okay, well, if the rabbit wants to go to the moon, maybe he's wearing a spacesuit, okay, one step in the right direction versus spacesuit. Oh, there's no spaceship around. Is he really moving in the long-term direction that he wants to go towards, right? And that's what we want to do. We want to evaluate the here and now, okay? And then we want to evaluate the longer term strategy, or really moving forward to that longer term goal towards our business. We also talked about the sampling process. Very, very important and fundamental in data science and data analysis. And we'll get to hacker statistics eventually in later classes that really help cover this concept in a lot more detail. Okay. So we talked about the different types of samples that we can take: multi-cluster, simple random sample, multi-stage clustering. And we do all of them because cost versus benefit. Some of them are much cheaper to get, but ideally we'd like to sample everyone in the population, but we can't sample, that's not usually possible. So we decide on a way that's reducing the bias that we'll see. We're trying to get a sample that represents the population while still a kind of cost-effective way to do so. We talked about the pandas in the environment, right? We're standing outside of the zoo, the pandas environment, and we saw all those pandas raining from the sky, filled up the pandas environment. It's important to remember that that's still just a sample. So we'll really learn to take to heart as we go through our classes is this, that we're always dealing with a sample, and that will affect the robustness of the answers that we find. We briefly touched on what a data frame is, or data matrix, and that's really when we turn information into data, when we give it that square shape, that structure, and it provides structure to our information, it turns it into data, just like our data here is providing structure to our panda. We touched on different data types. In a broad category, there's numerical and there's categorical. We talked about numerical having two subcategories, integers and floats, whole numbers and decimal place numbers. And then categories being ordered and unordered. And that will have a very large effect on how we analyze those categories, even leading into machine learning, how we would pre-process them. So it's really important to understand what type of category we have. And we'll cover more of this in the third class, what we briefly touched on. We want to understand the relationships, right? And as you can see here, there's lots of relationships in our data that we could understand, and it's likely very time consuming to understand everyone. So we want to kind of have our theory, we want to stay focused on what is our goal of this analysis and which relationships pertain to that goal. Okay, what are we really trying to understand? So, and focusing on understanding the relationships. Okay, I'll see you in the next video to get started this class. Hello, and thank you for joining me for the second class of our Data Analysis Bootcamp. So today we're going to understand distributions. Very important, kind of the first part of this, really where we're starting here, is, well, why are they so important? Why is it important to understand distributions? So why are distributions important? Really a beginning place of our data exploration. We want to understand our distributions to really see if we can start to identify patterns, things that are interesting, things that are worthwhile exploring a little bit more. So that we can also have an idea of how maybe things like our mean, our median will be affected by the shape of the distribution. The shape of the distribution is really strange, but it always surprised me, but it seems like it's more, well, it turns out to be more important to understand the distributions in your data than it is really to understand what the data represents in real life. You make good and deliver good insights. Now, that being said, you want to eventually understand what it represents in real life, but a much faster way to get to your insights is really understanding the shape of your distributions. We want to summarize the data, right? We generally don't want to say, oh, our distribution is an exponential distribution shape. We want to give summary statistics. We want to summarize the distributions usually down to a number, standard deviation, mean, mode, variance even. It's a little bit more digestible for people just to hear a number than it is, okay, we have a distribution. That's to bimodal distribution with the long right tail. It doesn't mean as much to people. It means more to me, but most people would say, oh, mean or average or max or min, those things. So we really want to understand our distribution to understand how those summary statistics are affected by the shape of the distribution. And this will lead into doing hypothesis testing is very fundamental, has a lot to do with the samples that we covered in the last class, and that randomness that is kind of baked into our data set that we can't really see or observe, but what is there, right? So the shape of a distribution will lead into how we're going to perform hypothesis testing. So it's really important to understand what we would want to do and how we're going to accomplish our hypothesis test by understanding the shapes of our distributions. So to help us remember this, let's imagine we are a data analyst showing up for work on Monday, let's say, and we're going to work. And what we want to do is we're sitting down at our desk, and can I ask you what colors is the desk that you're sitting down at? Mine's brown. I'm sitting down at my brown desk right here, and really when we sit down, we're going to start exploring. You can see here, there's a great picture of what are we going to explore today, right? We would start with our distributions to help understand, we could explore this whole valley, right? All of the data, all the hills and the valleys of our data. But that would take a long time. We probably don't have that much time, and our boss needs to report tonight. So we need to understand, we're really kind of sitting down to explore. We're going to go look out and start to understand where we want to go and what we want to explore. Okay. As we're sitting at our desk, we have a really nice poster up on our desk. That's really there. It kind of very nice. It looks like this. It's really there to help us remind us that we're always trying to find the summary statistic, right? We're really being conscious of that. We're really trying to refine down the information to more manageable, digestible, bite-sized pieces. But we have to be careful that these summary statistics can be very deceiving sometimes, and so we want to understand the shape of our distribution so that we can understand how the summary statistic is affected by these, or maybe we should choose a different summary statistic, mean or median or mode. What would make more sense? Variance or standard deviation? What makes more sense in these situations? Okay, and we want to make sure we're communicating properly. The end user probably won't understand the difference, or might not understand the difference. It's our responsibility to make sure that we're providing the best representation of our distributions for our business partners. And then as we're sitting at our desk, we're looking up at our poster, we have a nice view of the data that we're going to go explore. There's bang, bang, bang. Kind of annoying. I don't like loud noises like that. I don't know about you. Have you ever had a noisy neighbor or office neighbor? Have you ever had a neighbor at your house that's made a lot of noise? Just won't be quiet sometimes. Me too. And I think what they're doing that's where they do the testing over there in that room over there right next to us. That where they make the loud bang, and that's them probably getting out of their frustration as they're doing the hypothesis testing. Okay, and so it's very important though we understand why they're doing that, but it's a little bit noisy to be next to the room where they perform the hypothesis testing. Okay, so moving on. So another reason that we wanted to understand distributions is we want to use them as the more that we understand our distribution, we can get a sense of really where or what we would define as an outlier, where it would start, what we could well, where we would define what the starting point is. An outlier in exponential distribution might look very different than an outlier in a normal distribution. So we use this to help us define the shape of the distribution, to help us define really where it starts at the threshold of where we would say this is now. Okay. We also want to understand the skewness and the curtness. Is it leaning one side or the other side? Is it really skinny or is it really fat? We want to understand the shape of our distribution. These will play into the statistics. If it has a skew one way and a long right or left-hand tail, we want to understand that is going to be affecting very significantly in that case something like an average, right? And so maybe in those situations we want to, now that we know that the shape of our distribution has a skew and it's a little bit off to one side and a long right tail on the other side, we want to be using a median instead of, or maybe the mode instead of the average, right? So these are little simple things, but we really want to understand the shape of our distribution and define it really in skewness or kurtosis. One of the things that I like to do when I get started with my data analysis, I like to plot lots of the distributions, not necessarily to look at them side by side, but it's just something that happens is as you start to understand the distributions, you can see, are there similar patterns happening in each one? Is this repeating over and over again? If you were to see one exponential distribution, yeah, it's not a big deal, but as you start to see lots of them, you can almost be sure that that would be a financial data set. That's my background in financial exponential distributions are not my favorite now. Truthfully, I used to just they were everywhere in finance, but it's one of those things that exponential distributions, been really noticing that you see them a lot. Sort of that pattern can give you a lot of sense about what you'd be expecting from other distributions as well. If you notice things, you're expecting these patterns, these things are all looking similar. Are the same patterns repeating, right? Or are they not repeating? Both of those can be very enlightening and help guide our analysis of. Okay, so to help us remember these points is, when was the last time you saw the moon? You remember, where were you? Were you out with a friend, or were you out with at your family's house? Me, the last time I saw the moon is I was just outside of my apartment actually, and I saw the nice big moon up in the sky. And really think about that moon, and all of a sudden you notice as you're looking up at that moon, data is falling down. Kind of weird, huh? And we know that's outlier data because, well, that doesn't really happen often. It's really going to help us remember that we want to understand our outlier data. We want to define that threshold. I said that was outlier data, right? So I have to define my threshold when data is falling from the moon. Call that outlier data, right? So that's really where it starts. Maybe not surprising that that's where we would define our data. We also want to understand as the data was falling down, our visions start to get skewed and a little bit blurred, and I'm kind of wondering really, are we seeing things correctly now? Could we maybe not be interpreting the world around us in the correct way? And as we see our friend, a good old friend that we've had for a long time, starts walking up to us, and well, we gotta get a little bit concerned then because the vision's a little bit skewed. We're not interpreting the world correctly. And so we're kind of concerned that this skewness and this kurtosis could be affecting our future relationships, our relationships with our friend who's walking up to us. The data is falling down from the sky. Our friend is walking over to us, and well, this data is really making things, or the skewness, this outlier data is really affecting the way that we're seeing the world. And so we just need to be conscious of that and make sure that we're presenting our summary statistics in the correct way. We're being as clear as possible in light of imperfect distributions. Okay, so we talked a lot about why distributions are important. And from our last cast, it's always really important to remember that our distributions are still only a sample. This picture is a really good example of that, right? From a distance, it looks like a lot of people, but as you get a little bit closer to this image, you can see the individual people, right? So we always need to keep that in mind when we're dealing with the sample. And our inferences, our summary statistics, the shape of our distribution, all of that summary statistic is not the final. We want to take that summary statistic and understand the population. So we're really making inferences about the overall population, and it's really important to keep in mind as we go through this class, as we go through as we are data analysis. So we start to perform real world analyses. Those are posed on a sample. We will start to come to see the effect that those has, and we saw it in the first class as well, the variation that is caused by taking a sample. So I just wanted to touch on a powerful tool that we're going to be using in our data analysis called the histogram. It's so simple, but it works so well in really understanding the shape of our distributions. The idea here is we're going to decide on a number of bins that we're going to put our data in, and we're going to choose a set number of bins. And within these bins, what's going to happen is they're going to the function, the histogram plot, is going to choose or count the number of times data falls within each bin. What this really does is it removes a lot of the vibrations that happen in between data points and gives us a better view of the shape of our outside data. So you can kind of see that the steps here, little bins, we're putting our data into bins, and we can really see that outside shape to get rid of all of the noise around our data. It turns out that too much detail is not great for your analysis. You actually find I'm a very curious person, and I always wanted to really get into the details, and I still like to. But for communicating results and where you really start your analysis is there's too much sometimes. You get lost in that noise. You're not able to focus on the bigger picture right here. When we're getting started understanding our distributions, we want to understand really the shape of our distribution. Is it skewed one way or the left? Does it have a little tail? Are there outliers? We don't really want to see these little tiny vibrations, which really could just be caused by the fact that we have a sample, smaller sample than the overall population. And maybe in the population, this noise couldn't exist, right? So not getting rid of it, but choosing the amount. And one of the things that we'll have control with is the number of bins, so we can choose how much noise, how much generalization we're causing in our data analysis. Really good for communication, really good for presentations, and it's simple, but it's one of the ones that I would use the most. It's really a great starting point for any data analysis. So let's get into the types of distributions. There's lots of types of distributions. We're going to go over the four major types, and we usually use these as a starting point to describe and communicate what we're seeing. We could get really technical, but often it's better to stay a little bit simple in the sense and stick to the major categories and then describe the deviations from those categories. Okay, so we have uniform distribution. This is where each value is equally likely to occur. So this is our histogram plot. So this is our bin. and we're counting the number of times that our data occurs in that bin. Okay, and we can see roughly it was equally likely to occur. And really what that means is that we'll be able to, we have values that are occurring roughly about the same. It doesn't have to be exact, right? But again, rough. It's a good starting point for any type of flat distribution, be the uniform distribution. You can see our Python friends here. Please remember this. They're all wearing the uniforms. They're all exactly the same. So they're all equally likely. They're all the same. So that's the same thing. Every bin here is again equally likely to occur. We have our normal distribution here with the sides, and really the key feature is that it's symmetrical on both sides. We don't see a skew in a standard sense. We have our normal distribution. It's the bell shape that you probably have heard about in school before. And so much of natural science revolves around normal distributions. Finance can be approximated in a lot of ways with normal distributions. It's a really common thing. And as we'll get to in hacker statistics, there's some quirks in math that actually cause this in the resampling process as well. So fundamental, really important distribution to understand and get your head around. And really the idea here is that we have symmetrical, and we would usually describe this as, oh, it has a tail or it has outliers on the right-hand side, where it's kind of skewed to the left. It's a little bit more kurtosis, and that it's a little bit more skinny, or we could say it's even less kurtosis and a little bit flat, right? So we can describe these distributions many ways, but normal distribution is a really good starting point. Never really find the perfect normal distribution in your data, but you can find semi-normal, close to normal distributions. You can see our Python here, another Python friend here, our symmetrical Python friend here, and it's equal on both sides. Not perfect, but that doesn't really often occur in real life, but it is symmetrical, more or less symmetrical on both sides, and that's our normal distribution Python. Okay, so we also have an exponential distribution. This is really common in financial data sets. It has this long right-hand tail right here. It is honestly my least favorite distribution to deal with because it causes lots of problems where, as you can imagine, something like the average is really pulled to the right-hand side of the data set, or the right hand by this tail. And so the mean would, the average would be somewhere over here. And that's becomes where really the average is sitting where it's not really the weight, the density of the data is over here. And so because the average doesn't describe really the center, well, it decides a center, but not really where the weight, where the bulk of our data is. And that can create some problems in our statistics and really the interpretation from. And so this is often occurs when there's a time between events. Stock market returns follow this exponential type distribution. Okay, and you can see our Python here with this long hand tail to help us remember about the exponential distribution. We also have categorical distributions. You don't really think about categories being distributions, but really they're such an important one in data science because we can use these in so many different ways, use them to analyze our data, to classify our data and do different analysis, get really into our data a little bit deeper with these categories. And so understanding the balance or the imbalance that exists in the categories is a really important step in our data analysis and really understanding the distribution in our categorical data sets. And so the categorical distribution becomes, again, a little bit more important than it would be in classical spreadsheet type of analysis. Here we have a black and white Python here to help us remember what the categoricals. We want to understand the categorical distributions in the data set. We also have many other types of distributions that we deal with. I'll let you read through these. I provided the slide below the video. And so Poisson, beta distribution, gamma distribution, chi-square distribution. It's important to be aware of these. I would say that it's more important to stick to the one of the four major types we're describing. It's easier to communicate. Some people might not really be aware of how these distributions evolve, what affects them. They're less commonly known outside of data science. I would stick to the common ones when you're describing them. If you really feel that is a better fit, a gamma distribution is a better fit, then you can use that, but explain really the gamma distribution with the long right tail that's causing this effect of certain things. The ones that you'll see probably the most common is the student T distribution. And what this is very similar to the normal distribution. It's a little bit more kurtosis in that it's a little bit fatter and it has wider tails. This essentially makes it harder to pass a hypothesis test, which is commonly used when we have data sets where we have a small amount of samples in our data set and still need to perform hypothesis tests. So it's again making it a little bit harder to pass a hypothesis test when we have less data. Really important distribution as well. Not important as the normal, but still very commonly seen. Okay, so what to understand from each type of distribution? And so when we look at a uniform distribution, I think one of the common ones that you probably like the most is where we see right here a value is occurring one time, occurs over completely across the data set. This usually means it's something like an index. It is not likely going to be usable if it only occurs once throughout the whole data set. There's nothing to be learned. There's no pattern there. There's no reoccurring pattern that can be understood. And so really this likely is a data set that or this column, this feature, it is not going to be useful in our data analysis. It's important to understand and just kind of eliminate that. We might need it to access data at certain points to find out where the data is if it's an ID column, but in our analysis, it's not so important. So we can kind of just save that for later, so to speak. Another thing that will commonly happen is you'll see these kind of abnormal types of distributions where we have two levels. It doesn't necessarily just need to be a uniform distribution, but here you see these two levels essentially with this. And so when that happens, you see your data analyst gentleman here, he's thinking pretty hard. And you don't want to, hurt yourself thinking too hard, right? So we see that there are two different levels in this distribution, and really that's the time that we want to talk to the expert. We can get really far with what Python can do, but at a certain point, you need to rely on your business partner. Why am I seeing this? This is an insurance premium. Likely could be related to some levels. The pricing system would make sense. Maybe age, and once you cross an age range, it just drops or it just increases. And that could be why we're seeing this distinct level in these distributions, on this uniform distribution. What to understand from a normal distribution? I think the biggest thing is that we look for is outliers. It really, is there long, really even tails, I guess that's sense. Is there something that's pulling the mean to one direction or the other direction? This affects so many things. So we really want to pay attention to how the outliers could be affecting our summary statistics, because that will affect something simple like a mean. It can affect the correlation, it can affect our machine learning models. So if you're doing a data analysis to support a machine learning engineer, much more important to understand the outliers and really focus on these. It always surprised me the effect they have, but it really does have a large effect. We can also use normal distribution as you can see here, we have kind of an abnormal distribution. I would say this is, to me, if we had more data, it might start to fill or become closer to a normal distribution. It might not though, right? So we can say this is a semi-normal distribution. Falls somewhat the normal. It's a quick way to really visualize semi-normal. Okay, so it's kind of roughly the shape of a normal, but I'm not going to expect it to be exactly, and that kind of fits us in. There isn't really a good way to describe something that's kind of funky looking like this. There's a specific name that's very unique distribution, but again, relating it to the closest proximity that we have for that distribution. So looking at our little outlier friend here, we always want to keep an idea like this outlier friend here. He's pulling the mountain, he's pulling the moon towards him. Kind of extreme, but outliers do have a really surprisingly large effect on our summary statistics and kind of everything up from there. So we really have to pay attention. I did not want to believe that when I started. It is data, but we don't want them to skew our analysis, and that's the problem. They do kind of our summary statistics adapt to the outlier versus the bulk of our data, and that's not really what we want to understand. We want to understand the majority of our data, not just the outlier situation. Outlier situation is maybe something we save, we compartmentalize and study by itself, or we do things to manage its effect on the distribution. So what to understand from each type of distribution? And so when we look at a uniform distribution, I think one of the common ones that you probably like the most is where we see right here a value is occurring one time, occurs over completely across the data. This usually means it's something like an index. It is not likely going to be usable if it only occurs once throughout the whole data set. There's nothing to be learned. There's no pattern there. There's no reoccurring pattern that can be understood. And so really this likely is a data set that, or this column, this feature is not going to be useful in our data analysis. It's important to understand and just kind of eliminate that. We might need it to access data at certain points to find out where the data is if it's an ID column. But in our analysis, it's not so important. So we can kind of just save that for later, so to speak. Another thing that will commonly happen is you'll see these kind of abnormal types of distributions where we have two levels. It doesn't necessarily just need to be a uniform distribution, but here you see these two levels essentially with this. And so when that happens, you can see your data analyst gentleman here, he's thinking pretty hard. And you don't want to, hurt yourself thinking too hard, right? So we see that there are two different levels in this distribution, and really that's the time that we want to talk to the expert. We can get really far with what Python can do, but at a certain point, you need to rely on your business partner. Why am I seeing this? This is an insurance premium. Likely could be related to some levels. The pricing system would make sense, maybe age, and once you cross an age range, it just drops or it just increases. And that could be why we're seeing this distinct level in these distributions, on this uniform distribution. What to understand from a normal distribution? I think the biggest thing is that we look for is outliers. It really, is there long, really even tails, I guess that sense. Is there something that's pulling the mean to one direction or the other direction? This affects so many things. So we really want to pay attention to how the outliers could be affecting our summary statistics, because that will affect something simple like a mean. It can affect the correlation, it can affect our machine learning models. So if you're doing a data analysis to support a machine learning engineer, much more important to understand the outliers and really focus on these. It always surprised me the effect they have, but it really does have a large effect. We can also use normal distribution as you can see here, we have kind of an abnormal distribution. I would say this is, to me, if we had more data, it might start to fill or become closer to a normal distribution. It might not though, right? So we can say this is a semi-normal distribution. Falls somewhat the normal. It's a quick way to really visualize semi-normal. Okay, so it's kind of roughly the shape of a normal, but I'm not going to expect it to be exactly, and that kind of fits us in. There isn't really a good way to describe something that's kind of funky looking like this. There's a specific name is a very unique distribution, but again, relating it to the closest proximity that we have for that distribution. So looking at our little outlier friend here, we always want to keep an idea like this outlier friend here. He's pulling the mountain, he's pulling the moon towards him. Kind of extreme, but outliers do have a really surprisingly large effect on our summary statistics and kind of everything up from there. So we really have to pay attention to them. I did not want to believe that when I started. It is data, but we don't want them to skew our analysis, and that's the problem. They do kind of our summary statistics adapt to the outlier versus the bulk of our data, and that's not really what we want to understand. We want to understand the majority of our data, not just the outlier situation. Outlier situation is maybe something we save, we compartmentalize and study by itself, or we do things to manage its effect on the distribution. Okay, lastly here we want to describe what are outliers, right? We talk a lot about outliers, and you'll hear me talk a lot more about outliers, and it's just the effect they have, right? So I can't be quiet about them because they're just very important. So try to drill that thought into your head. And so talking about here, a box plot is a distribution plot, a very simple distribution plot that is really meant to focus specifically on outliers. So what a box plot is the middle box right here, we call it the mid-range of the data. It goes from the 25th to the 75th percentile. And then 1.5 times that would be where the whisker ends. So 1.5, this interquartile distance, this mid-range right here, 1.5 times that is where the whisker will go out to. And anything beyond that is considered an outlier in the classical definition of outliers, which is a really good reason. It's good to stick to the classical definition because the way that you manage or the way you truncate or kind of massage your outliers, dropping them, it will have an effect on your final statistic. So I know that you can manipulate your final statistic by the way that you know, many acceptable ways to truncate your outliers. So I prefer that people stick to this classical definition so that I know there was no kind of funny business going on. You're really just you're being unbiased in your data analysis and you're doing what's generally accepted as a good way to truncate your outliers. And so it's going to go 25th to 75th percentile, and then that middle 50%, 1.5 times that will be our threshold for considering something as an outlier. Again, you don't have to use this. There, if you skew from this definition, you just want to make sure you have a justifiable reason as to why you would skew from the classical definition. Maybe you have a very good reason. It's just you would want supporting evidence as to why. Okay. Okay, and recapping our mnemonics that we used today. Okay, so we talked about our job as a data analyst. Remember, we were sitting down at that desk, brown, well, my desk was brown, color your desk was, but we were sitting down at our desk, whatever color that may be. Really, our first step is figuring out where we want to go from here, right? We want to look out and explore this data analysis or data so that we can understand our distributions and help use our distributions to help guide our analysis. Where do we want to go from here? We talked about, we had that picture up on our wall to help us remember, but really our goal is to provide summary statistics. We need to be aware of the distributions and how those will affect our summary statistics. Our business partners are not maybe going to see those distributions. They might not be aware of that, but we really want to make sure that we're delivering valuable information that's not skewed in any way that could be affecting their decision making ability. Talked about, we heard that noise too, like bang, bang, bang. Noise next door when you're trying to do our data analysis. Rude people next door doing their hypothesis test, but I understand it can be kind of frustrating and making a lot of noise while they're doing it, right? So a really important step in our data analysis as we deal with the sample, but again, it makes a little bit of noise when you're doing that testing. We talked about we were outside of our house or wherever you might have been when we saw the moon that one day. I was outside of my apartment and I saw all the data falling down from the sky. And it really, I decided I labeled that as outlier data. I decided that's my threshold that when data is falling from the moon, it's outlier data. And what we saw is that it started to skew our vision a little bit. It started to make it a little bit harder to see. So we wanted to be aware of how those outliers, how the shape of our distribution is the skew could potentially skew our distributions, our summary statistics, our interpretations. And we had our friend that was coming, one of our old friends was coming up to say hi to us, and he was a little bit blurry. It was a little bit hard to see him, and we were a little bit worried because of this all the data that's skewing our vision around us. We're a little bit more concerned. We have to be very clear, and we want to try to make clear and concise communication with this because might be affecting the relationships in our data, and so we have to be careful about the skew and the shape of our data. Those outliers can be really tricky. We discussed that really what we're trying to do is make an inference on the entire population as a whole. Okay? We have a small sample. We're trying to understand the whole population. We often do this, or a good starting point in our data analysis is the histogram that gives us a good sense of removes a little bit of the noise and helps us approximate more the shape of the distribution. The noise can be good, but that much detail usually is almost unnecessary. We want to understand a bigger picture type of understanding. The histogram helps us do that quite well. Although not always. Sometimes you want to understand less detail, and we'll talk about that in later classes. We can get really that high level amount of detail. We talked about different types of distributions. We had an equally likely occurring type of distribution. Do you remember which one that was? That's right, the uniform distribution. We also had a distribution that was symmetrical. Do you remember what type of distribution that was? That's right, the normal distribution. We also had one with a long right-hand tail that, remember I said many times, not my favorite distribution to deal with. Do you remember which one that one was? Right, the exponential distribution. And then we had a distribution. We often look at the balance in the category. Kind of give that one away, but do you remember which one that distribution was? right? The categorical distribution, which one, and really understand really the big four main types of distributions, and we'll use those to approximate shapes. When we're trying to describe our distributions, we'll use those to approximate the shapes of our distribution. Okay. We talked about what to understand from different distributions. When we had a uniform distribution, and when we see really things that didn't make sense, it's time to say, sometimes we can get really far with data analysis, but there's going to be a limit. And so it's very humble, and we want to say, it's time to talk to an expert really to understand this in a little bit more detail. We talked about a normal distribution and how, talked many times already, how we said about the outliers that often occur in a normal distribution. We have tails and how they can really pull, like this outlier gentleman right here is pulling the mean, so the mountain and the moon towards him. Outliers really have a large effect in pulling statistics towards them and adapt to what works for the outlier, sacrificing what really the bulk of the data would provide. We talked about how to deal with log distributions exponential distributions, and we can take the log transformation of those, which would turn an exponential distribution back into a an exponential distribution back into a normal distribution, which is much easier to deal with, can give us a better statistic. A normal and an exponential distribution can be a little bit deceiving in the answers we're seeing, good or bad, but what we're seeing is when we do a normal distribution and a log transform exponential distribution, so they're much similar to both being normal now, we get a much clearer representation of that correlation. We do other things like bucketize and put our exponential into buckets and remove the effect completely of that long tail. We did touch on what outliers are and how they are in the box plot. We have our mid-range of data, our interquartile range, which is the 25th to the 75th percentile, and 1.5 times outside of that is our classic definition of an outlier. And it is really good because we'll see in later classes the effect of the way that we manage our outliers can have on our summary statistics. And so it can provide a little bit of skepticism about your data analysis if you're doing a little bit too much to massage your outliers, because as you will find out, you can really massage them to give you a good answer or a worse answer. And so it's good to stick with this classic definition unless you have a really solid reason as to why. And some of the things that we talked about, the mnemonics that we used, unique, illogical, lots of colors. We connected everything to past memories, time that we saw the moon. And these are really important. We kind of told a story through them. So that will help us draw us back into these points. And I used colors a little bit as well. I find colors have a little bit less, but they're there. They're there to kind of draw us back and make it easier to find them. And the thing is, you won't really notice these. The information will just be there like it should be. Use words association to help connect those two, give us a little aid in coming back to those memories. Talked a lot about location and space when I was telling stories. I really kind of talked about there. Really using 3D space, and that's just how our minds work. We remember things a little bit better when they're 3D spaces. I wanted to mention that there was a lot of writing on those slides that I didn't read that, and so it would be really good if you could go back down the slides or go back up and view all the slides that this class, read them a little bit, and make sure you understand. Hello, and thank you for joining me for the Python notebook in our second data analysis bootcamp. So today we're going to go over the car crash data set, and we're starting with the standard data science libraries, pandas, numpy, seaborn, and matplotlib. Okay. Here we're importing I'm just starting with two different colors to sign those, just so I can play around with them as we go through our data set today. Easier just to set them in advance. Pull those as we go through our class today. Okay. So we talked a lot about distributions to show us how to generate distributions in NumPy using the random sublibrary. So numpy.random uniform, making a uniform distribution from 1 to 100, size 500. And you'll see as we plot this, be different every time. Gotta make sure I run everything in order. And you'll see as we plot this, it's going to be different every time. We run this. And this is using NumPy's pseudo-random function that allows us to plot it in a way that is going to generate, it's not necessarily random, but it's pulling it like as if it were random, and we could, if we wanted to, control this random in the future. And this is the same thing that controls in machine learning the random state, and I'll save that for the machine learning. Okay. So just showing really, it's pulling it from a uniform distribution, but even though we only have 500 samples, you can see it evolving. It's not perfect though, right? And that's the point. So it's kind of a semi-normal, almost normal, and almost uniform distribution. You're not going to find perfect things, but we're using the classical definition as a starting point to define this, right? And really to help us understand it and really to communicate what we're seeing. Normal distribution, we would use the numpy random dot loc equals 1. So this is saying the location, it's centered at 1. Standard deviation is 2 points, so 2 points up for 1 standard deviation, 2 points down for -1 standard deviation, and a size of 500. And you can see even an outlier, a little bit of an outlier guy over here, right? In a normal distribution, this is entirely possible. It could occur 3 standard deviations away at 1% chance, but it's possible all the way out there. Okay. And we're going to just plot this and looking at using a box plot just to highlight the outliers that we're seeing, just to see, do we see outliers, where do we see them? And what's interesting here is with this classic definition of the 25th to the 75th percentile, we have a little bit of an outlier over here. Maybe that one's pretty obvious to see. We also have an outlier over here as well. Just a little bit, I guess 7 is where we're seeing an outlier right here. It's this guy right here that we consider an outlier in terms of our mid-range of our data, because we have so much data right here in the middle. If we were to do a much bigger one, let's say 5,000, you start to see this will evolve into much more of a normal distribution. Again, still some outliers here as well. So what we did with those for our statistics, and then we'll see the effect that these have in later classes, because they really do, they are substantial, and you'll hear me talk a lot about outliers. And the box plot is a good way to just not think too hard and just what you see is what you get sort of thing. Here we're focusing just on the outliers, and these are what they are, and it's a good way to truncate or to manage them based on this plot like we talked about. An exponential distribution, there's a couple different exponential distributions. So the one that we discussed, the one that we generally mean is a standard exponential distribution. And here, plotting that looking at 500 samples as well. And again, not perfect, but getting there. Doing more samples, I'm doing here 50,000 samples. And if we were to plot, we discussed binning this, and we could use, I wanted to show this plt.avx line. This works because Seaborn and Pandas plot as well are made with the matplotlib library. Okay, they just call it, they do lots of fun things, fancy things. So we need to do a lot of formatting, editing, and things like that. We often have to call the matplotlib library to format things on top of the Seaborn. I guess they're really Seaborn is meant to work in the way that you'll go back to matplotlib often to do a little bit more of the formatting styles, things like that, adding 2 plots together. And here's what we're doing. I'm just kind of picked some bins here, so we could do 5, 1, 2, 3.2, and just looked at the bins and kind of getting good spacing here. Where would I want to, if I were to bin these and turn these into categories, where would I start to bin them so that the data becomes roughly equal in that sense? Okay, so this is a visual way to inspect this and to really understand where you're getting this. So we have an exponential distribution here. Let's see what a log transformation does. Okay, so we're going to go log numpy.log, and this is probably one of the most common reasons that I use numpy is this log transformation here. So sample equals numpy.log, and here you can see when we plot this, it's not perfect exactly. This is not going to be, it never really works out to be perfect. So you usually have to do a little bit of truncating or bringing in these outliers over here. But now we have a distribution where the average is going to be much more representative, really in the center of the data instead of somewhere over here, like it would be with an exponential distribution. Okay, just to show that all the other functions that we have, random distribution generators that we have, we can generate from the logistic generate distribution. And I have notes about what these are down below, so Poisson as well. A little bit more looking for integers, and here we're looking at a gamma distribution. Okay. Gamma distribution is kind of doesn't start off high, it starts low and then goes high. So you see this? And I'll let you read through these on your own time. You don't have to listen to me read stuff to you. You're a big boy, I'm sure you can do it. So going through these. And these are common-ish. You'll hear about them at least. You're not really going to run into them a whole bunch while you're getting started. And so I don't really go into a lot of detail because really this is about being practical. What's going to make you a good practical data scientist? And mastering statistics is helpful. It's always going to be helpful the more that you understand about statistics. Is it going to make you a really good data scientist today or data analyst today? I would say probably not going to be super helpful. The students treat T distribution as an important one to be aware of, as it might affect our hypothesis testing, or it's a good distribution to use when we do not have a lot of samples and we want to make our hypothesis test a little bit harder. This is a better alternative than the normal distribution. This is a little bit more spread out. Okay. And getting into the car crashes. So looking at our car crash data set today. Okay, so pretty standard. This happens when you see this unnamed category. What happens is when this was saved as a CSV, person or whoever did it forgot to say, I don't want the index, these index values brought into the data frame. And so you'll often see this. This is usually something you can just drop. We don't need to know this, but you'll see when we plot this, we get an unnamed distribution, a very uniform and equal distribution. This is where you know really not going to be able to use this in any way. Yeah. So walking through how I did this, all these plots and these distributions. So for featuring DF columns, what DF columns does is it gives us a list of all the column names. And so we're going to walk through this. And again, you could probably skip over this first one if you wanted to. If we wanted to redo that and just not plot this first one, what we could do is we could start at the second column, so position number 1, until the end, and go like this. And now we're going to essentially miss them if we wanted to. Okay, going through all of these. I have pretty abnormal distributions in this, and outliers over here. Really, it would be nice to know what's an outlier in this. We see this abnormal kind of 2 levels of the uniform distribution, some pretty weird distributions in this data set. Worked out really well for this class. I think this is a really good idea. Even if this is my own project for personal sake, I would still write these notes right here. It's going to be my to-do list for what I'm going to do in pre-processing, what I'm going to need to do to manage and manipulate, what I want to look for, what I've noticed and stuff like that. It's just, you can go back to these distributions. It is a lot easier to just come back to your notes much quicker and faster. It'll save you, even if it's only 10 seconds, it'll save you 10 seconds every time you come back to this. And that could add that time, those things will start to add up over time. Okay. So just writing down little short notes about what I see here. I'm going to make the next thing, I'm going to make an outlier tag. I wasn't sure there was outliers, so it'd be good to kind of just build a function to highlight those quickly. And it would be great for a presentation just to have kind of the outliers highlighted as this. Just be a little bit nicer in the presentation, a little fancy. So what we're going to do here is we're going to go define outliers tag, outliers underscore tag. We're going to be using this with the dot apply function. So this first position is going to be the value in the row at the time. So I'm using this right here. What this is going to do, this function that we're creating right here, is dot apply is going to be iterating through all of the rows. It looks like it happens all at once, but it's actually a recursive function. So it's going row by row by row, and every row is going to take the value out of the row and then pass it to this outlier text. It's going to take the responsibility of managing this for us. And so the value in this first row is going to be the value in the row at the time. Just to initialize this, I'm setting a lower bound and an upper bound, which will be my interquartile based on the interquartile range. And we'll see how I do it. Okay, so if x is lower than the lower bound, or it's greater than the upper bound, we're going to assign an outlier, and else it's a normal, right? So it's not on the extremes. This is where or is good when you're looking to classify the 2 tails of your distributions. We're also going to use numpy.percentile here to give us the quartile, the interquartile range here, so the mid-range of our data. So 25, so I give it the distribution of my data, the whole array, the one-dimensional array, and series in this case, and then I'm going to go with the 25th and then the 75th. So those, you can see here, just gives a nice float number. To find the interquartile range, then it's the bigger number, 75 minus 25, and that gives us our interquartile range. I can then go, my upper bound is my interquartile range, or sorry, my 25th quartile minus interquartile range times 1.5, interquartile range plus, or sorry, the quartile 75 plus 1.5 times the interquartile range, my upper bound. I'm going to use that in the dot apply function. Notice these are part of the outlier tag function, but I'm not passing them directly to this. I'm passing it to the dot apply function. It's going to take responsibility of passing those to the outlier tag. So it's really the dot apply's job, the kind of boss of this operation. And then with that, I get outlier tags right here. I can now very clearly see what's an outlier. Maybe this one wasn't so surprising, but we very easily identified that. Now, I kind of built this. It would be nice if we put this into a function, make it a little bit cleaner and easier to use as we do other things. Okay? So here I'm just going to put these, making the quartiles and getting the interquartile range, applying this to the function. What I'm going to do here, this is kind of interesting, so that I was able to do this in a loop. This is probably the hardest part of this function, because what happens is when I give this palette color to this function, it needs to be the right number of, I need to give it a list of the right number of colors that I have in my plot. Okay, now with this, sometimes I have one, and as we'll see when we go down, sometimes I don't have any. So sometimes I do, and sometimes I don't. Okay, so when I don't, I only want one color, and when I do, I need two. So what I did then is I got the number of categories. I went and found the length of the outlier, then the feature, the category that identifies outliers. How many different values are there in there? One or two. And then depending on that, what I'm going to do is I'm going to give this a list of color 1, color 2, but I'm going to then give it numcat, my lines like this, okay, numcat. And so what this will do is if this is a 1, it's going to go 0, 1. So it's going to give it the first value. If it's 2, it's going to go 0, 1, 2. So it's going to give it the first two, 0 and 1, not including this one. Okay. And then I'm going to highlight my feature based on the feature that I just created up above and add a title and then show my plots. Okay. Run this and we can see here we got a nice color right here. So a little highlighting the tag on this side right here. Okay. Or sorry, the outlier on this side right there. Okay. So now we can just very quickly, easily iterate through the whole data frame using our feature outlier tagger. So 4 feet in div columns. I missed the unnamed and missed the object columns right here. I have a couple ones where I won't be able to tag those outliers. And I'm gonna print and just make sure when I was building this, it just helped to understand how many categories I had in my outlier class and to see which one I'm going through each time. Okay. So you can see this each time. And sometimes I have an outlier and really easily highlighting those, and then in speed, I don't have any outliers. And not distracted, I do have an outlier over here, and in lots of the other ones I don't. Right? So it's good to now identify those very quick and easy, and a cool little plot that we can. Another good thing, we talked about this with the exponential distribution, but understanding non-linear relationships, it can be good to bin our continuous variable and really inspect that, use that to change the colors and see more of another distribution and inspect to see if there's a non-linear relationship. Things that a correlation analysis might miss. So what I do here is in define binner, I'm going to go edges equals numpy.linspace, give it the min of my feature and the max of my feature. And this I'm making the edges. So if you have one bin, you're gonna have 2 outside edges. If you have 3 bins, you have 3 bins, you'll have 4 outside edges. And so how many ever bins I'm gonna have 1 more outside edge. And so what I'm gonna do is bins plus 1. So I want 3 bins, but I'm gonna actually have 4 outside edges. I'm gonna go labels here. And these labels, depending on it, we're gonna iterate through this and select which values I want. Okay. To do the binning, I'm going to go pd.cut, give it my feature column, I'm going to give the bins the outside edges, and my labels, which will be the names of my bins, just calling A, B, C, D, just to make it not too complicated. So this will work kind of indiscriminately for any function, just kind of generically calling the bins. So what I'm going to do here is I'm going to go for the number of bins that I want. I'm going to get the range of this, 0, 1, 2, let's say there's 3. Let's go for I. So I is going to come into my labels right here. It's going to go 0 first, select A, select B, select C, and give those 3 values right there and build a little mini list of A, B, C. Or if I have 4, I can be 0, 1, 2, 3, and so it's going to go select 1, 0, 1, 2, 3, and then you kind of give an ability to change the color or change the number of labels that you have based on your bin. So it's a very flexible little function in using a list comprehension. Okay, and those list comprehensions are really handy when you need to do something in a small, compact way. Okay, so just to iterate through this, it's for I in range, or in the number of bins in my list of 0, 1, 2, 0, 1, 2, 3, and we'll be pulling that I from my labels to make a list. So A in, B in, C in, and so on. Define my binner. And I wrote some notes just on how this worked as well, so you can definitely read this up if you're missing anything that I spoke. Sorry if I went a little bit fast. Looking at our total bins, I'm gonna just in this case I'm just gonna look at the total and see if that has a maybe non-linear relationship with the rest of my data. You can see the length of the bins that I got, the number of values in each one. And if I look at the sns.kde kernel density estimation plot, giving it my full data frame, giving Seedmore likes to have access to a full data frame, and you can just go x equals one column, hue equals another column. So I'm going to change the color by this hue. Do line width to 3, just make it a little bit thicker. It kind of makes it a little bit look nicer. And the bandwidth method. So this is going to say, show me a little bit of detail. Don't completely, if you turn this really up, it's going to smooth this completely, and you might not get a sense of really where the data is. This is going to say when you drops right here, this is because the bandwidth is turned down a little bit. I'm able to get a truer sense of how much data is actually there. This is a little bit more texture. Turning it down too much kind of makes things a little bit confusing and stuff. So there's kind of a good amount that you can play with. What's interesting is, to me, this looks like it has a very non-linear relationship. There's A is in really right in the middle. So the smallest total is in the right in the center right here, and this kind of spreads. B goes up and down from this value, really where the weight of those two are, bimodal distribution there. D is really spread out, a little bit more weight to the right side. Okay, C is spread out a little bit more weight to the left side. So this is very much not a linear relationship. We probably get a very low correlation. But it's interesting. There's definitely something going on with this total category and this thing. So warrants more inspection. Looking at not distracted as well. This maybe is not so telling. It's kind of interesting that for only the A column, there's this bimodal, and D as well. There's this bimodal little hump right here, and another mode in our distribution here that would be interesting. And here as well, so lots of bimodal distributions when you're classifying by total. Really interesting. It might be worth inspecting a little bit. Might be the time to talk to an expert and see if he has an explanation why we would be seeing it. Could be something to do with the pricing of the insurance, something to do with the way the system works in this sense. And looking here, this I would say is a little bit more of a linear relationship. A is a really small number, B, C, D, so not anything substantial in this one, but you do see a lot of these bimodal distributions again, which is very curious that we see those so often. So we're starting to notice a pattern between our distributions, and that might be worth inspecting a little bit farther. And speeding here, so you see this one as well. This has a kind of a funky little thing going on here. We have A over here, really short, little bimodal. Bimodal is kind of the theme of this. Bimodal for the B, bimodal for the C. And the thing is, they're not happening in the same place. This is something that we could miss if we didn't bin the category and inspect it by this other distribution. It's really interesting. I wrote some notes here to kind of go into a little bit more detail about what I was seeing. And this is really the starting point. You could go so much deeper to really start to understand why these are, and I challenge you to play around with this and see if you can find some more interesting details about what we discussed. Use kind of your knowledge of Seedmore. So we're going to spend a lot of time going over all the little fun things that we can do with Seedmore. This is a really good way for us to get started and to understand this a little bit. Thank you so much for joining me today, and I will see you next time or in the next class. See you next class. Bye.